wait, yeah, okay. Okay, so tell me.
Automorphism of Z2 cross Z2 is isomorphic to S3. You have to show that.
Okay. So already this Z is what I was considering that day. Yeah, I was considering some Z mod something and Z, right? So already came here. Automorphism of Z2 cross Z2 is isomorphic to S3. All right. So, well, I would suggest you do like this indirectly rather, little bit. First, you show that, let's call this G. Show G is non-abelian. Okay. And second, show size of G is 6. And then you just use that there are only two groups up to isomorphism for order 6, right? So number of groups of order 6 up to isomorphism, I mean, are only two, are 2. Okay. All right. And one of them is abelian, the cyclic group, right? And then the other has to be this. So if you prove it's non-abelian, then it is this. So what I will do is I will leave this this two for homework, right? And let's do this one of them. Let's do this one. Fine. Yeah. So show that it is non-abelian. Well, you know, this can be done by linear algebra, in fact, because these are actually vector spaces over field of order 2. So, but anyways, yeah. But you can basically use the inspiration. I mean, what I'm saying is that you say that, okay, you want an automorphism, right? So you want a function from this to this. And what you can do is, means what you should be looking to do is to decide where 1, 0 goes and where 0, 1 goes. Yeah. By the way, I am assuming, of course, I mean, that's the only thing that makes sense, but just to make it clear, we are doing it under the addition. Under multiplication, it's under multiplication also it's a group, right? Because order 2, but I think we are considering under addition. So you have to just decide where to send these two things, correct? And you want an injective function. So where can you send this? That's the question. So how many options do you have for this? 3 choices. You can't send it to 0, 0, 0, otherwise it will not be injective, right? And then if you send it to 3 choices, then this is 2 choices. Right? Is it correct? For example,
Yes,
if you send this to 1, 0, then you will have to, yeah, okay. I mean, you will not, you can send this to this, you get identity. And similarly, you have the other choices. So automatically problem in part 2 is also solved. Okay. I mean, that way, right? You get the maps and you just show that they don't commute, right? So for example, you can just take 2 maps and show they don't commute. Which 2 should you take? Just take, for example, you send this to this and you send this to 1, 1. This will, but you should check that this gives you a homomorphism. Okay. Yeah. If you don't want to use more theory, which at this point it's fine, you should check. If you're like writing this in an exam, it's good to just check at this stage. So you have this map, and then you just think of some other map, and it will not commute with this, unless you pick the trivial maps. If you pick identity, then it will obviously commute. take some other map, like some opposite thing and so on. Right? There are many options, right? 6 options. So yeah, you can show that these two don't commute. How do you show? Well, you just compose and check, right? So you take 1, 0. This one is still 1, 0, and then this one becomes 0, 1. So finally it becomes 0, 1. If you do it the other way, what does it become? This becomes the 1, 0. This becomes 0, 1. And then phi 1 of 0, 1 is 1, 1. So it's not equal, right? So it means that these two functions are not equal. So this implies that phi 2 compose phi 1 is not equal to phi 1 compose, because they found something where, and so it's non-commutative, right? And if it's non-commutative, it has to be S3. But if you provide it, you do this homework. And this is a very easy, trivial fact. Or you can directly write all the things and then say that it is S3. Check that it is S3. Yeah. If you want to directly show that it is S3, see, the problem is that, yeah, I mean, you can also directly try to show, you can use group actions, maybe. So this is fine. This is one thing, but what I want to say is, yes, I'll just keep this as it is. See, the more conceptual ways, I think even silos, when we were doing silo theorems, we were doing this kind of thing. So you are looking at automorphisms of this, right? Automorphisms of this. And you want to show that this is S3. So what you can do is you can find an object X on which you will make this S3 act. Okay. In this case, what should that object be? That is the question, right? So for example, you can take this object to be 3 vectors. In this case, the vectors can be 1, 0, 0, 1, and maybe 1, 1, right? Take these 3. So X is this set, right? Now, sorry, not S3 that we want to show. So let me not write S3 at all. You want to show this. I'll just write this 2 here, meaning it's set 2 cross set 2. This is actually I use standard notation. So, okay, right. So the plan now is that you make this act on this. Okay, make this act on this. And through that, we can try to understand the group. How? So, well, you know that the size is 6, right? And yeah, so there is, yeah, I can say that, but let me first say it concretely here. So you make it act on this, and then you see what permutations you're getting. What permutations of X are you getting in this way? Okay. So you take the different sigmas and you make them act on this, right? And what permutations of this thing are you getting? And you can show that, yeah, you get all permutations. Or at least you show you get all transposition. That's also good enough, right? You know, transposition generate permutations. So you can do it in any number of ways. You know, you can use all these different styles. But I mean, maybe this opportunity can be taken to introduce this concept of free actions. Okay, free actions. This is, I think, this is important. This can be very useful actually. So, because mostly anyway, let me just say what this is: free action. So, in terms, it's like free in the sense that there are no. I mean, you don't actually do any quotients, any stabilizers. There are no stabilizers. Okay. So yeah, basically I can just write that, no stabilizers. Yeah. There is also something called transitively free, but actually that is just words on top of words, but it's not complicated. It's just transitive, free and transitive. But what is a free action? Free action is no stabilizers. What does that mean? So can anyone define what free action should be? I've already said it here, but like what will the defining terms be? How would you say? So G acts on X, right? There's a G, then there is an X, such that the action is there. We say this action is free if G dot X is never equal to X. Yeah, for any, so maybe I could have written like that, same thing, but for all G and for all X, right? Sorry, yeah. For all G and for all X, G dot X is never equal to X. That's what I just wrote, no stabilizer, right? So that's the point. So, I mean, you can kind of understand that this is it's a complete, it's like completely, the group is completely there in the space in X. Right, what does this mean? So you can do, I'll give you an exercise, you should do this. From the, so this will make you better in group actions, and actually that's what you should be getting. So think about this. So let G act on X transitively. So again, you may have to look at the definitions, but they will all, you'll find all these definitions in Intermittent Foot or any algebra book. Acts transitively and freely, right? And then you can let this be true. Actually, there is nothing to say, but show that this is true. This is very simple, and this is okay, but main thing I want to say is put a natural group structure. So you can, I'm saying you can actually make X into a group. Okay, you can actually make X into a group. Okay, put a natural group structure on X. Yes. That you should try to prove. And then I'll give you a more concrete example in R2, and that also you can try. But just, just maybe note this down, because that problem is an example of a free action. Yeah, because the identity map is the only map that fixes all the points. So I mean, of course here I mean G not equal to identity, of course. Yeah, otherwise it's true. Otherwise it obviously fixes, but yeah. So this is the general concept, free actions. Okay. I'll also give you a visual example of this thing. So this is fine. And let me just give you this. This actually, so for example, how would you, so if you take x1 and x2, then how would you multiply them? That can be the question, right? So how would you multiply them? So well, this x2 will actually be equal to some g dot x1, because it's a transitive action, right? Transitive action. Right. So how would you basically the question here is how would you define this multiplication, right? Okay, so that's the question. Okay, so there are two elements in this set, and we want to understand how will you define this multiplication. What should you return? You have to return an element of x again. What should you return? Yeah, so I mean, I will just return g dot x1. Okay, and now the game is like this. So it's like I'm defining the group action with x being my center of focus. X1 being my center of focus. Now if I take x2 and x3, what I will do naturally is I know that for x2 already I said there is a g such that it is g times x1, right? And for x3 also there is another g such that x3 is g times x1. And so what I should return? Well, there is only one natural choice. I'll return this. This will be another element in the group, right? But there are some things to check here and check them. but probably it's if this thing is a like little confusing, I can write and make a concrete question here, which is like a standard, which is a more exam friendly type question way to say it. Yeah, show. Okay, so I'll write it here. So this is equivalent. This is equivalent to saying that given x1 comma x2, there exists a unique. That's a symbol, right? There exists a unique. Yeah, not exists is that there exists a unique. Okay, maybe I just write there exists a unique G in G such that G times x1 is x2. This actually, this is a very simple exercise, will there in any book also, but I'm just mentioning. That's what free means, does nothing is fixed, but at the same time, it also means that, if you want to go from one place to another place, there is only one path to go from x1 to x2. There is only one G which takes you from, there's only one edge, any paths, but there's only one edge that takes you from x1 to x2. So that's that's the essential feature of a free action. So this is the nice things. I mean, with free actions, you can actually put a structure on and this is actually very useful. When you actually have topology, then you can actually put a topological structure on the space from the group if you have, but those we will see later. Now coming to a concrete example, obviously that example is there, but for example, you can think about this. You can look at R2, right? You can, yeah, but yes, but that is actually not very enlightening. Let me not get into all that. It's same stuff over and over again. So these are the things which are there. Yeah, that's it. Maybe let me not say more things here. Yeah. Okay. Now, if you would like to view this from the angle of vector spaces, that also you should do. Okay. If you would want to view this from the angle of vector space, this is actually this is actually asking for all the invertible 2x2 matrices over F2. Actually asking you to count that and say what that is. So maybe that is something which is somewhat interesting. So you can look at this. So well, if you're looking at so yeah, this is going to be this is actually very interesting because yeah, maybe I'll just say it like this. So for example, you have Z2 cross Z2. Maybe just take a few more Z2s so that it's more interesting. 4 Z2s, okay? And then same thing. So okay. All right. Now, what do you know about this? You know that this thing, let's say that this is, well, it is just this, right? Just writing it like that. Well, you know that this is a group, right? Is a group, correct? Yes or no? Right? This is a group, right? This is what the starting thing is. The next point I want to make. So you understand Z2. Z2 is also a field, right? Z2 is a field, right? 2-element field. Z2, usually it is called F2, is a field, right? That's okay. Now, third thing is that Z2 4 is, I'll now call it as F2 because I want to emphasize the field structure. F2 is a F2 vector space, right? This is the viewpoint. That's how you use the linear algebra you have studied, right? Is a F2 vector space. Otherwise, everything looks very dissociated and disconnected. Is an F2 vector space. Just do the most obvious things, right? And F2 vector space, the addition which you do here is coordinate wise, which is how you do in R4, which is how you add in group also, right? So vector space with same group structure. That's the point. Same group structure. Yeah. Should look at these things. This is the same group structure. Now that's the main thing which I want to say now. Let phi. Okay. Phi is a group homomorphism. What does it mean? It just means it's a function which satisfies some extra properties, right? But the cool thing is, phi is a group homomorphism is the same thing as phi is a linear map. Linear transformation is the standard word for you. So linear operator because it's from the same domain to same range. But this is the main thing which you should realize really quickly. And if you don't, then you should check it out. You just write it. I mean, it's a function, right? So I mean, if this is a function which you clearly know, then what more do you need to check that it's a linear transformation, that under scalar multiplication something happens? Just check it. Just write it out and check it. This is really the key. Yeah, this is the key. Module theory and everything starts like it's useful, but this is very, very simple stuff. This thing. So now, if you have that, then of course, phi is an automorphism. This is just a consequence. What does this mean? This means that this phi automorphism is invertible, but it's also already a linear transformation, right? Yeah. So this means that phi is, I mean, I'll just say an invertible matrix. Now we get into matrix. Linear transformation means a matrix. When given a basis, we take the standard basis, and then it's a matrix, right? Is an invertible matrix. This is the catch, that counting automorphisms here is counting the number of matrices, and these are all 0, 1 matrices, favorite matrices, right? Like them. 0, 1 matrices is not a problem, right? Now you see the fun. So all this is connection with linear algebra. It's a same straightforward thing. So this is the invertible matrices. So I mean, so what is it that we have to do now? So then the problem becomes that count the number of invertible 4x4 matrices with coefficients coming from F2, meaning that you're just addition modulo 2, right? Nothing else over F2. This is the problem, right? And this is actually a very simple problem. You can just count it by hand. You have to just use the fact that it's invertible and the rows are linearly independent, and using that you can just count it. So no, it is not correct. Right. Okay. And then I'm proposing that what you can do is you can replace this 4x4. This is now just a red, so I mean, this is also simple, but I mean, this is something that people, I mean, do in first year in itself. Many people do in the first year itself. So it's actually simple. So you should try this out. You can replace this 4x4 with n by n, okay, matrices. And here this invertible is invertible, okay. But you do it over any field, any finite field. And here finite field means it has size p to the n for some prime p. So actually this is easy to, this can be, okay, easy and hard, I don't know, but this can be counted. Means it's in Damuton foot. That's my point. It's in Damuton foot. That's so it's elementary. Okay. But further we can generalize this, and you can take all this and see if you can. And actually that next one can be solved using group actions. Okay, straightforward. Just make the group act on space. Yeah, just make GLN that group which you want to. Yeah, just using orbit stabilizer formula you can count it. And what is that? So you see now you try to just bend this and look at it. So try to just see, mix it up with the linear algebra that you know. So if you're looking at invertible n by n matrices, I mean, just think of this as a field, right? I mean, you can keep, if you want, this is a field. You can just say that's just an F. You don't have to actually think too much about it. If you don't know much finite fields, don't worry. You don't need to in this case. Okay, it's just the field. It's just the set in which you have in multiplication and division, inverses, and so on. So it's just the field. You can just keep R in mind. Only that if you take over R, then it becomes infinitely many. So you don't have to count anything. But here it will be finitely many, and the counting becomes a good question. But this thing FPN is there. But what I'm saying is that what is an invertible n by n matrix? It is n rows, right? It is n rows. N rows which are linearly independent, correct? N rows which are linearly independent. So it's basically an n tuple of bases, right? Yeah, it's basically the number of ordered bases, right? Because so what I'm saying is that every invertible matrix is basically, if you consider the rows as the vectors, the rows are vectors, right? Then this is actually an ordered basis, correct? Because it's linearly independent, that's the definition, right? It's an ordered basis, correct? Any linearly independent set of size n is a basis, right? And it has concrete coordinates and everything, so you don't have to worry about anything. It's a basis of what? That's the question. So that's something I wrote here wrong. The basis of which space? Is a basis for, right? So it will be a basis for what? It's a basis for, this over this field, you have n. That space. I mean, if it was R, if reals, R to the power n. I mean, so you have n vectors in Rn, and they are linearly independent. So that's the basis of Rn. That's all I'm saying. But in this case, Rn is getting replaced by Fpn, this field. So it's an ordered basis, right? So this problem is counting the number of ordered bases. That's all, right? But this is an easier problem. But then, so yeah, so this is counting the number of ordered bases. But then you see, every time you take ordered bases, instead of that, you can count number of ordered k. Okay, that k is not appearing. So ordered k linearly independent sets. Now this is just some extra things. But this is also, actually, this is simpler, right? I mean, you have to just count the number of, so instead of, instead of going all the way, to count, find a row, then find the row independent from that, find the row which is independent, so that all three are independent, and so on till Rn. What I'm just asking, you have to stop at k and count how many ways you can do this, right? This is something which you can also, is easier actually. But then next question becomes that now, when you have started to count k linearly independent sets, then every k linearly independent set determines a subspace of dimension k, correct? But two different k linearly independent sets might determine the same subspace, right? They might determine the same subspace. Agree? So now you should think, when do two linearly independent sets describe the same subspace? Right? And that happens, but when? Or when means how many? That will basically be the number of, so you have two linearly independent subsets and determining the same basis. That is basically the number of k linearly independent subsets of this k dimensional space, because all of them will not determine the same k dimensional space. That's the ulta view, right, which you have to take. So I mean, that is the thing, but finally you can actually take this as an abstract, and this question will come tomorrow, and count the number of hyperplanes will come tomorrow. So this is the question, that count the number of k dimensional, how many n dimensional spaces are there? One. How many one dimensional subspaces are there? Number of lines. How many two dimensional? Number of planes. I'm asking how many k dimensional subspaces are there. and the number is finite because you're over a finite field. Interesting, right? This is also elementary. But the next thing becomes, which is something which I tried to study in the summer. I went for a workshop for that, and that becomes, like count the number of points in intersections of these spaces with certain interesting conditions, and they become what goes into what is called Schubert calculus. This is where it's really the pinnacle. And then after that, there is something called enumerative geometry. Not after that, I would say, but yes, somehow it's considered more advanced geometry. I mean, I don't know these things, okay, but I learned a little bit, but yeah, this I certainly don't. Okay, so it's a very interesting host of things, and this probably takes years of training to learn this kind of things. Okay, but anyway, we'll stop here and then we'll meet after 10 minutes and we'll do some other problems. You look at these things and see if you have any questions. And but please work out all these you can easily work out, and even these are easy. Yeah, this is actually a standard question. Actually, you'll find in RT and miscellaneous actually. Okay, yeah, in operators. So anyways, we'll meet after 10 minutes and continue.